My dear student, colleagues, and all the viewers who are watching this program live from Facebook page Physics Adda, I'd like to welcome you all to our International Physics webinar. Today is our 41st Physics webinar. Good afternoon to all here in Bangladesh, and also good afternoon to all those who are watching from India. Hope you are well and safe from Corona pandemic. So we are living in a Corona pandemic situation, and all the institutions have been shut down due to the Corona pandemic, and we cannot continue our normal academic program inside the campus. So we have to start our online program. So our Department of Physics, Pabna University of Science and Technology, have started some online program, including online classes and online physics webinar. And you have already come to know that we have arranged a series of international physics webinar. And in those physics webinar, physicists from different countries are coming as a main speaker, and they delivered their speech and they shared their knowledge with our student. And I think by this way, our students have benefited. The main aim of our webinar is to motivate and encourage our students in this Corona pandemic situation. And today, I'd like to welcome you all to a joint session between Pabna University of Science and Technology, Pabna, Bangladesh, and Inter-University Center for Astronomy and Astrophysics in Astrophysics and Astronomy. And we have with us here today Dr. Somak Raychaudhury, sir, Director, Inter-University Center for Astronomy and Astrophysics, Pune, India, connecting with us from Pune, India. So he has already connected with us. Sir, good morning. Sorry, good afternoon, sir.
Afternoon.
Yeah.
Good afternoon.
And welcome to our physics webinar, sir. And I'd like to say thanks on the I'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, sir, for accepting our invitation.
Thanks.
I think it's a very good opportunity for our students to interact with such a big astrophysicist like you. And I think they may learn a lot of the new things today. So for those who are new, I'd like to inform that we have divided our webinar into 3 parts. First, I'd like to introduce our speaker with all of you. Then our speaker will deliver his speech for our student. And at the end, we have a discussion time. In that time, actually, anybody can join with us by using the link. And you can also ask questions by commenting. So I think you have already come to know the title of our today's physics webinar. So, and our speaker is Dr. Somak Raychaudhury, the future of the universe, Mahabhishet Bhavishyat. So if we see our Somak Raychaudhury sir, Somak Raychaudhury sir is currently working as director at the Inter-University Center for Astronomy and Astrophysics, Pune, India. So he has graduated from Presidential College, University of Kolkata, India, with further studies at the University of Oxford, UK. After his PhD from the University of Cambridge, UK, he worked at the Harvard Smithsonian Center for Astrophysics, USA, where he also part of a team that built the Chandra X-ray Observatory for NASA, now celebrating 20 years in space. After teaching for over a decade at the University of Cambridge, UK, returned to India as a head of the physics and Dean of Sciences at Presidency University, Kolkata, before he became director of IUCAA. Dr. Raychaudhury's research involves a wide range of topics in cosmology and astrophysics from the ground and from space. He is known for his work on stellar mass black holes and supermassive black holes. His significant contribution includes those in the field of gravitational lensing, galaxy dynamics, and large-scale motion in the universe, including the Great Attractor. So if we see his education, scholarship, and prize, you can see he completed his bachelor degree from Presidency College, India, and then BA Physics from University of Oxford, UK, and then PhD from UK. And scholarship, he got about 4 scholarships from different institutions and prize also. So if you see his career, he actually now currently as a director of IUCAA, but he also worked as a dean of the Faculty of Physical and Mathematical Science and the head of the Department of Physics, Presidency University, Kolkata, India, and Faculty of School of Physics and Astronomy, University of Birmingham, UK, from 2002 to 2013. And in 2007, he was working as a visiting professor at Harvard Smithsonian Center for Astrophysics, Cambridge, MA, USA, and so on. So he's also a member of International Astronomical Union. And if you see his Google Scholar ID, we can see his citation number is more than 5,000. So we are very proud actually that the physicists like him actually accepted our invitation. So sir, thank you again, and it's your time, sir. You can start your session, sir.
Thank you, Pretam. It's a very good afternoon to everybody, wherever you are in the world. And thank you for this very resounding introduction. I hope I can do justice to it. I'm sharing my slides right now. So what I decided to do is that because I was just told that there will be quite a lot of international members in the audience, as well as people who are not conversant with Bangla. So what I will do is I will say a few things in Bangla. Only one of my slides is actually in Bangla, and I've kept a few things in Bangla in the talk, but I'll give my talk mainly in English. So people who don't understand Bangla, please don't think that this is a talk that's been given in Bangla. You will understand. I will say a few things in Bangla just to for the benefit of the people who are listening. Which I want to point out a few things in Bangla. Okay, anyway, so my talk is about the future of the universe, Mahavishya Bhavishyat. And in doing this, what I want to know, what I want to tell you is what we know about the universe as a whole right now. And I know that this has been a long series in which there have been quite a lot of people who have talked about various aspects of astrophysics. And some have talked about cosmology, some have talked about galaxies. If you listen to Paolo Salucci's talk, he would have talked about dark matter. And I will actually repeat some of that, because I don't believe everybody here would have listened to all those talks. And I will repeat a few of those things, because I need, in order to talk about the future of the universe. And by the future of the universe, I don't mean what's going to happen to it tomorrow, but what's going to happen to it in billions and billions of years. I'm going to use some of these concepts of what we know about the universe, in particular what we know about the matter and energy in the universe, in order for us to understand what's going to happen to the universe. So as an astronomer, I was introduced, I work at the Inter-University Center for Astronomy and Astrophysics in Pune, and I am an observational astronomer. I observe the universe in all kinds of ways, and using many telescopes. So normally what you do is, if you look at the sky, this is the traditional way of observing the sky, and you see the stars. This you can see with the naked eye, right? But what you do is you can observe the universe in all kinds of light, not just light that is sensitive to the eye, but in all, and these are all called electromagnetic waves, তড়িৎ চুম্বকীয় তরঙ্গ আমি লিখেছি ওখানে, এবং এই তরঙ্গের যে spectrum, the Bernoulli of the radiation, it comes in all kinds of ways. I mean, you can see that our eyes are sensitive only in the middle here, as you know, the visible light, which is a very tiny part of the whole spectrum. And in the whole spectrum, and for thousands of years, till the 20th century, this is all we had access to. First with the naked eye, and then with telescopes. And so we knew only a very little part, very small part of our view of the universe. It was very, very tiny. We really couldn't really see the universe very well. And as a result, we didn't know much about the universe. And so that is why astrophysics is a very, very young subject. People knew a lot about the stars, but they didn't know much about the universe. Because in order to study what's in the universe, and you've heard a lot of examples, you have to study them in all kinds of light, be it X-rays, gamma rays, and here what we have is wavelength in meters, and you can see Of course, these are a few hundreds of nanometers, which is what our eyes are sensitive to. But on the low energy side, you have the radio waves, and on the high energy side, you have the X-rays, and you need the information from all kinds of this spectrum, and you'll see examples of that. And as an observational astronomer, I study the universe in all kinds of these ways. I use giant radio telescopes. Here in Pune, we have one of the world's largest radio telescopes, the GMRT, and I study the universe with it. I study galaxies and supermassive black holes with it. I use X-ray telescopes in space, and gamma ray telescopes and ultraviolet telescopes in space to study things and use them with light, and together find study the universe. So it's very, very important to bring in all kinds of astronomy together. That is a very important thing that we have to know. I wanted to, the only Bangla thing I'm going to talk about today is about how, as a Bengali, we came to know about the universe through the writing of some of the best writers that we've had in our language. And in particular, because some of the earliest Indian scientists, physicists, got interested in this whole spectrum of electromagnetic radiation. One of them was, of course, Acharya Jagadish Chandra Bosu. And Jagadish Chandra Bosu started working on radio waves and microwaves in particular, and got the people around him interested, and Rabindranath Tagore was one of them. Rabindranath Tagore wrote an amazing book, and people here who can read Bengali but haven't read Rabindranath's Vishwa Parichaya should see how, from the 1930s and 1940s, even the people who are not initiated into Vigyan, into science in general, have been reading about what lies outside the light we perceive. And this is an extract from Rabindranath's Vishwa Parichaya, published in 1930s. He of course passed away in 1941, and you can see he's talking about the sunlight, that's the visual light that you see, but on each side of it you have these amazing different parts of the electromagnetic spectrum, the beguni, oti, nil, and he came up with these amazing words for these kinds of light. For example, infrared light he called lal ujani alo, oti nil alo, which is ultraviolet in beguni. এরম ধরনের তো এই যে আমাদের বর্ণালী, এই বর্ণালীর আমাদের চোখে আমরা যে আলো দেখতে পাই তার বাইরের যে বর্ণালী, এটা নিয়ে অলরেডি আলোচনা শুরু হয়ে গেছিল সেই সময়. Jagadish Bose started working on radio waves, microwaves, and people realized that outside our traditional way of looking at the universe, there are other things. Jagadish Bose tried to, for example, detect the sun in the radio wave scale, but he actually did other things. And then slowly, within a few years, we realized that we can, if we can send things up in the atmosphere and outside the atmosphere, we can look at the universe in other parts of the spectrum, right? So now what we can do is we can look at the same sky with the naked eye, but if we actually build large telescopes, and here I'm come back to the optical light. This is a view of the same sky through the Hubble Space Telescope. And you can see that what you can do, the reason you need telescopes is that you can go very far away and look at the deep sky and look at very far away objects that you need to do in order to study the universe. So here are whatever you see in this part of on the right hand side, the picture is the picture that you see with the naked eye, khali chokher akash, jekhane you see only tara, only stars, and then on the other side you see what we call galaxies. Because if you really look at the deep part of the universe, you don't see the stars anymore. You're looking at a small part of the sky but going very deep. And here there are only two stars, that one and that one. There are two stars, the rest are galaxies, and each galaxy has billions of stars, 10 to the power 10, 10 to the power 11 stars, right? And So then we realized, and only in the 1930s and 1940s, we realized from the work of Hubble and Shapley and others, that we actually live in a universe where the basic building blocks are galaxies, right? And these galaxies are like molecules in matter. They are the basic building blocks. And within each galaxy there are all these stars. And so what's happening in this picture is that we are looking through the screen of stars which are in our own galaxy. Our own galaxy is called the Milky Way. And this, of course, has a checkered history. I'm going to quickly talk about how people understood this. And this is part of this whole story of understanding how the universe is built. In the late part of the 18th century, there were these two people, one in England, William Herschel, and the other in France, Charles Messier, and both of them were studying stars that didn't look like stars. They didn't twinkle. They are fuzzy objects in the sky, and they both independently made catalogs of these fuzzy objects in the sky for different reasons. And Herschel, of course, was building at that time the biggest telescopes in the world in his own back garden, even though he was an amateur astronomer. He was a musician, but in the evenings he built these big telescopes. Nowadays, of course, that is not possible. You cannot have an amateur astronomer build the biggest telescopes in the world. Charles Messier in France had his own telescope, and they built these large catalogs of things looking through these telescopes that did not twinkle, but they were extended objects, right? We know about the Messier catalog. Any amateur astronomer knows about it. And for Herschel, the catalog is called the Ngc Catalog, the New General Catalog, which we all use now. Now, these are now modern pictures of the same objects from these catalogs. All these four objects here are in both catalogs, in the Messier catalog as well as in Herschel's catalog. And you can see that they are very, very different objects, right? Now, with our knowledge now, 200 years later, we can look at them 300 years later, we can look at them with a lot of resolution and see that, for example, that all of these are kind of the same size on the sky, but they look different because they're different distances, right? And so here, for example, M1 is actually a single star that has exploded. It exploded in a supernova 1,000 years ago, and it's called the Crab Nebula now. It is a single star, but it's exploded, and because it's exploded, the debris looks like a fuzzy object in the sky. Similarly, M27, which is on the right, here you can see that it is actually a star that has not quite died, but a lot of matter has come out of it. It's still a single star. It's called a planetary nebula, but it's a star. So M1 Crab and M27, they are both single stars. Whereas if you look at the top object, which is M3, it is actually a globular cluster that has 1 million stars. প্রায় 1 কোটি তারা। এবং তার নিচে যেটা M51, it is a galaxy that has 10 to the power 11 stars. And they all look like the same through a small telescope, and they are the same size on the sky. And that is because in order to find out what these things are, you need to know how far away they are. And one of the fundamental problems in astronomy, which we'll talk about today, is to find out how far away things are. And that is not an easy thing to measure. If you know how far away, for example, the sun and the moon, they're exactly the same size in the sky. But one is 1,000 times more distant than the other because one is 1,000 times larger than the other. But they look the same on the sky, same size, half a degree. Similarly, all these things look the same on the sky, but because we didn't know how to measure distances to these things till about the 1920s and the 1930s, we did not know. So Messier and Herschel thought that these are the same things, whereas Hubble, as you will see, and Shapley and people like that in the 1930s showed us how to figure out what these things are. And now we know that then the universe is made up of galaxies. The galaxies are, as you can see, the M51 Galaxy here is like our own galaxy. It contains 10 to the power 11 stars, and these are the building blocks of matter of the universe. And about 25% of all galaxies are elliptical galaxies. Paolo Salucci would have talked about this in his talk a few days ago. And then most galaxies are very flat. They are like spirals, and they are flat galaxies. Our own galaxy looks like this. From side view, it is very, very flat, routine moto. When you're looking at, you know that the sun, the Earth is on the sun, around the sun, and it's not at the center. It is quite a bit offset from the center. In the plane of the galaxy, there's a lot of dust. If you look at these are of course pictures drawn by artists. You cannot take a picture of the galaxy from within our galaxy. If you look at the galaxy from the top, then this is what it looks like. It's got these 5 spiral arms, and the sun is in the Orion arm. And the sun is going around the galaxy. It has gone around 20 times or so, like that, as the galaxy turns very slowly. This is what we know. So our spiral galaxies, which are flat, they turn, they rotate, but they rotate, and the stars within them sometimes rotate much faster than the galaxy itself, and that's what the sun is doing right now. And actually, you can see the sense in which the sun is rotating is this. It's going around like that. And this is why when we see the Milky Way from inside, this is a picture taken from a telescope in Chile. I'll come back to this telescope later on. It's a very important telescope. But what happens is that because we are looking at the Milky Way, our own galaxy, from the sun, the Earth itself blocks much of the Milky Way. So we from Bangladesh or India don't really see a very good view of the center of our galaxy. We have to go to the southern hemisphere. So this is taken from Chile. You go to South Africa, you go to Australia, you can actually see the real glory of the Milky Way. You can see that that's, if you look at all this kind of dust that's in the middle of the galaxy, those are the things that you can see in there. And these are 2 satellites of the Milky Way, satellite galaxies. We have moon galaxies that go around our galaxy. Okay, and if you go out a little bit, you know, our local neighborhood is such that we have 2 of these big spiral galaxies: the Milky Way, which is our own galaxy, jake amra Akash Ganga boli. Akash Ganga is our own galaxy, and then we have Andromeda, jar Sanskrit naam Debjani. Debjani or Akash Ganga, the Milky Way and Andromeda. These are the 2 big galaxies, and these galaxies are falling towards each other with lots and lots of satellite galaxies with them, right? And so that kind of tells us where we are in our local neighborhood. And if you go out even further, you see that people have done now 3-dimensional studies of a distribution of galaxies, maps of galaxies, and you can see that there are lots and lots of millions of galaxies in this picture. And this is actually a slice through the universe in which each point is a galaxy. And you can see that the galaxies are distributed in a rather non-homogeneous way. It's very clumpy, and people call it a kind of a web structure, Makorsha Jaler moto, cosmic web. We also know that the universe is expanding. You get pictures like this in a textbook, which kind of shows that what is happening is that the universe, space-time itself is expanding, and the galaxies are as if they are embedded on this space-time. And so as the universe expands, then what we see is that the galaxies are going away from each other because the space-time itself is expanding. Now, this is a really misleading picture, though it is given in all textbooks. It kind of assumes that you have a balloon-like thing on which galaxies are there, but then you can ask the question, who's blowing into the balloon? And the geometry itself is very confusing. A better picture is the one that I show right at the bottom here, which is, for example, if you've ever made bread in an oven or tandoor or whatever, you know that you put a little dough and the whole thing expands. And if there are things in there like kishmish or some seeds, etc., they go away from each other. So you can think about the universe expanding as a whole as the universe, the stuff of the universe, the actual the space itself has a character, and that expands. And as a result, the galaxies themselves, which themselves are not expanding, they are just going away from each other. Right? That's the idea. And to do this, then, how was this established? I'm sure a lot of you know the story, but there are a lot of people here who have not been exposed to astrophysics and cosmology. For the benefit of them, I want to talk about very briefly about how one established this. One found that the universe is expanding, and this was done by Edwin Hubble, of course, at the beginning, working in America in the 1930s. And what he did was that he used what is known as the redshift of each object. What happens is that if you take, Bernoulli, the spectrum, you take light and you can break it up into the entire Bernoulli in the spectrum. And what happens is that if the elements that are in a particular star or a galaxy have a particular characteristic line that you can see in the Bernoulli, right? For example, helium has these lines, mercury has these lines, sodium has these lines, and physics students who are watching this will know that they have probably done this in their lab. So if you take, for example, this is the spectrum of a galaxy, and if you plot the brightness as a function of wavelength, then you will find all these lines, and some of them are dark lines, which are absorption lines, and some of them are bright lines, emission lines. Now, you know exactly what the wavelength of these lines are, and due to an effect called the Doppler effect, what happens, you can see it, you can have a hydrogen line, and you can see it directly there. Now, due to an effect called the Doppler effect, where the source moves, the actual wavelength changes, source moves away from you, the wavelength changes in a sense that it moves to the red, so the object it's shown as a redshift. So for example, if you can see that you know exactly where this hydrogen line will be at a particular point, this particular line, which is called the H alpha line, will be at 6,556 nanometers, and then you know exactly where it is. But if the source itself is moving, then it will move away from you. As you can see, here it is, you're taking it from the Orion Nebula, and you have this line that is there, but it is at 656 nanometers. But if you then observe it from something that is a distant galaxy, you will see that it's already gone and gone to a different 660 or more nanometers. And later on, you can see that as the galaxy is further away, it gets smaller, but you can see that the line in that spectrum is further away. It's gone to 670 and so on, right? So if you can see how as you're going from something that's within our galaxy, the Orion Nebula, to going to distant and more and distant galaxies, the line moves to the red and further and further. And this shows that as you look at galaxies that are further and further away, the velocity of the galaxy is moving away from us in more and more moving away as the actual magnitude changes, and more, as you can see. And this is what Hubble found in the 1930s. He plotted redshift, which is this motion away from us, as a function of the distance, which is kind of either relative brightness or some way of measuring distance. And he found that there is a linear correlation. This is not a very good plot. This is the first plot that he published, has a lot of scatter, but of course this has been repeated later on. So he found that the universe is expanding, and that's the only way you can explain why galaxies that are moving further and further away, that are further and further away from us, have higher and higher redshifts. And he found that almost all galaxies in the universe, apart from 2 or 3, which are falling towards us, are actually going away. So this can only be explained if the universe as a whole is expanding, right? Now then the question arises, what is then going to happen to the universe if it's expanding? Is it going to expand forever? Or is it going to expand up to a point and then come back, etc., etc.? And this is the topic of today's discourse. What I'm talking about is what is going to happen to the universe. How is the universe going to expand forever? This is something that Stephen Hawking, in his famous book, which was published in the 1980s, called A Brief History of Time, he discussed these possibilities, and this became very famous. I'm sure a lot of you have read this book it was published in many languages. I had the privilege of listening to the set of talks, because he was one of my teachers in Cambridge, the set of talks that led to this book. He gave first this as a series of lectures, public lectures, and that became a book. And everybody started talking about what is going to happen to the universe. The universe, will it come back? Because when you throw up a stone, it goes and it slows down, it goes up to a point and then it comes back, right? It does not go on forever. But if you launch a rocket, it often can go past the Earth's gravity and go up forever, right? So when the universe started in a big bang, and then it's expanding, the question is, what is going to happen to it? And the answer is then lies in knowing how much matter there is in the universe. Why does the stone that you throw up come back? It comes back because there's a gravitational pull of the Earth that is come. And if you throw the same stone on the moon, it is going to go very far up compared to on the Earth. And that is because the moon's gravity is lower than the Earth's gravity. So do we have, and that is why I've written here, it depends on the density of the universe. Do we have enough matter in the universe for us to understand whether the universe is going to come back or expand forever? And Hawking in his book said, for example, if the universe's density or the total amount of matter, energy in the universe is too big, then the universe will come back in a big crunch. And but if it's too small, then the universe, well, like this, for example, if you look at the distance between two objects as given by the metric on the expanding space-time, this is your distance as a function of time, and we are here now. So the universe started somewhere in the Big Bang in the past. This is negative time. Then what has happened is that if the universe has enough matter, it is going to come back and be a bound universe. It is all going to come back together, or it can go on expanding forever, and it's called the big freeze. It will be larger and larger and larger, and colder and colder and colder, and eventually it will become so large that no light, no life, nothing will exist. So which one is true? What do we know about it? So will it be the big crunch? Will it continue forever, growing at the same speed, or it will actually be the big chill? So in order to do that, what we have to know what what the universe is made of, what makes the universe. So what are we made of? Let's start there. We are made up of what we see in the periodic table, these elements, right? And these elements, some of these elements are important in what we are made of. And for example, our proteins are made up of carbon, hydrogen, nitrogen, phosphorus, sulfur, oxygen, things like that. And those things, and those are these elements here, and those things make mostly are responsible for us. But anything that we see around us is made up of some of these elements, right? But these elements are also made up of protons and neutrons, and these are made up of quarks. So we know that we are made up of quarks, and so these particles are called baryons. Now, is this what the universe is made of? That's the first question you want to ask. And Paolo Salucci in his talk would talk about how we went into the evidence of finding whether we are made up of the same things. And I'll repeat that argument. So, for example, so to do that, we have to find out the dynamical effects of the matter in the universe to figure out how much matter there is in the universe, right? And this started maybe in the 1950s, 1960s. For example, you know that if something moves like a solid body, like for example, a compact disc or one of these things that you play with in the park, the whole thing moves as a solid body, and then the orbital speed, the speed of somebody who is standing at a different distance from the center is going to go up in a straight line, right? V will be proportional to R because angular speed is constant. And that happens in the solar system, for example. In the solar system, if you go away from the sun, then you'll find completely different experience. It is not the same as this, right? For example, the solar system does not move as a whole like that. In the solar system, what happens is that all the mass is in the center, in the sun, and as you go further and further away, the force due to the sun on the planet decreases, and as a result, the centrifugal force, which is essentially v squared over r, it goes down because the force decreases. And so what you have is the orbital speed, if you plot it against the distance, will fall off, and it falls off as 1 over square root of r, Pabna might have talked about. Whereas here, the orbital speed goes up as r, it goes up. So clearly, in the solar system, the whole thing doesn't move as a whole thing, right? But what happens in galaxies? If you have a galaxy like our galaxy, which looks like this, and you're in the center, and maybe the sun is somewhere here, do all the stars move all together like that? Or it moves like the solar system? Because, of course, as you can see, these two are very different. In this case, in the solar system, all the matter is in the sun, and the planets are very tiny compared to the sun. But in the galaxy, the matter is all distributed. But is it distributed like this? And this is something that people started measuring in the 1960s. And the idea is, how is this rotation of the galaxy happening at different parts of the galaxy? And this is Vera Rubin, after whom a telescope has been named recently, as you know. She passed away a couple of years ago. Vera Rubin, in the 1970s, was working on her master's thesis. And in her master's thesis, what she did was she tried to measure the rotation as a function of distance in 5 spiral galaxies. And what she did was this. She looked at radio emitting hydrogen gas. If this is, for example, a picture of a spiral galaxy, and you can see the optical picture, the real photograph of the galaxy right in the middle in the form of a negative. But all the stuff that you see around it is what you get from a radio telescope. It's radio emitting, it is detection of neutral hydrogen that is around the galaxy, that goes far away from where the light is, out to about 4 or 5 times the distance of the galaxy. And you can take that, you can measure the rotation using Doppler shifts if the galaxy is inclined to the line of sight. And she did that, and she found that in the center of the galaxy, V as a function of R went up, just like here I showed you, which is like a solid body. But outside, as you went out, you would have expected the rotation curve, the velocities, to fall off, like in the case of the solar system, but it did not. It kept on going and going and going and going, and stayed completely flat. And this meant that in the outer parts of the galaxies, where the stars stopped, they are absolutely flat. There is more matter there. And without which, what would have happened is that as you went outside the galaxy, the velocities would have dropped like this, right? It's expected from that. But she found that there was a lot of matter outside, and she called this dark matter. And so this difference between, if for example, galaxies only had stars, like we see, then the rotation curve that Vera Rubin measured would have dropped off like that. But she saw that they were flat, and that meant there's a lot of matter on the outskirts of the galaxy. And if you do that, it just shows that in almost all galaxies now, we've now measured this, not in 5 galaxies, but in hundreds of thousands of galaxies. The same thing has happened. What we find is that in the middle, it goes up like a solid body, and then it flattens off and never comes down. We haven't found a single galaxy in which it's come down. Paolo might have told you a couple of his experiments with galaxies in which maybe they have found some that come down, but we haven't found the edge of a galaxy yet. It keeps on going and going and going. And it just means that galaxies lie in big halos of dark matter. And this dark matter is what the galaxy is made of. And only in the middle, right in the middle, we see some stars. So here's the point. The point is that we know how many baryons, how many quarks there are in the universe. And if all this dark matter that is in all the galaxies in the universe behaves like this, then the universe cannot be made up of quarks. Dark matter cannot be made up of baryons, which are protons and neutrons that are in the periodic table. It has to be made up of something completely different. And this is what we came to know in the 1960s and 70s, the universe has a lot of matter, but that is not the same matter that we are made of. That is not made up of carbon, nitrogen, etc., whatever, which has quarks in them, which has protons and neutrons in them. And this is when we realize that the universe is made of dark matter. I'll give you another example, not just from the spiral rotation curves of dark matter, but here's another way of doing it. You know, Einstein showed us one very interesting thing, and that is that that if you have matter in the universe, then it curves space-time. And as light passes through that curved space-time, the light itself bends. And so, for example, if you have the sun, which is like this, and then the sun goes and you have what it does is that it bends space-time, and then what you have is that if you have a star somewhere and an astronomer is observing the star, what will happen is that it sees the light coming by the sun or a star or a galaxy or whatever in a bent way, but actually to the astronomer it will appear somewhere else. So this causes a mirage. এটা মরীচিকার মতো, যেখানে একটা আলো আসছে একটা জায়গা থেকে, কিন্তু যেহেতু space itself is bent, সেহেতু we see the star or the galaxy somewhere else. And that is exactly what happens. It's a prediction of Einstein's theory of relativity. When we see something from the Earth and we look at a galaxy that is very far away, the light that is coming to us is being bent by the amount of matter that is in between us and the galaxy. And as a result, light bends. And we see distorted images of that galaxy. We see the galaxies in different places, but not just that, but it also becomes distorted. And we can study the distortion and from that infer how much matter there is in the universe. This is an effect called gravitational lensing. Here's an example of, for example, one of my friends, Sarah Bridle, who works on these things, produce these amazing images of what happens if for example, there's matter between her and I watching her going through, and you can see that if it's matter that has the shape of, say, a galaxy, then you will get multiple images of the face in all oriented in different ways. So, for example, if you have a source field like this, it will be oriented in various distorted ways. And by studying these distortions, assuming that there is some regularity in the original image, you can find out how much matter there is in between us. So you can find out how much matter, for example, there is in that cluster of galaxies. And these have been seen. So, for example, if these things are aligned perfectly to each other and you have light coming from just behind another source of another massive object, then it can be seen to become a whole ring. The galaxy or a star will become a whole ring rather than a point object. And that's because it's all aligned. And this was all predicted by Einstein's theory, but from the 1960s and 1970s, we have started to see these things. These are observed Hubble Space Telescope images, or ALMA and Hubble Space Telescope images of these things. As you can see, we can find a galaxy. So, for example, this galaxy is in the foreground, and that galaxy which appears as a ring is actually in the background, and we are seeing it. And so by studying how big this ring is, this Einstein ring is, we can find the mass of this galaxy, right? And it turns out the mass of the galaxy is many times larger than the light that is coming out, right? And so we now know that clusters of galaxies, these are very good examples of gravitational lensing, and these are clusters of galaxies which produce these amazingly distorted images. You can see, for example, here that galaxy and a galaxy on the other side, they are the same thing. We see 5 images of the galaxy, and by looking at the distortions and the different images that are produced by the galaxy, we can measure how much matter there is in this cluster of galaxies. It turns out there are a few hundred times more than the light that comes from the stars in the galaxies. And so there is dark matter. And we now know that there is and there's lovely examples of gravitational lensing due to galaxy clusters have come out of the Hubble Space Telescope images over the last few years. So The dark matter itself, and you've had talks dark matter before, told us till about 1995, when I was finishing my PhD and starting my astronomical career. That is when a lot of things changed. We were still wondering how we live in a universe that is made up of matter, which is not even like us. It's completely different. It is not made up of quarks. We don't know what it is. And it seemed to make up much more. There are 10 times as much dark matter in the universe, maybe 100 times than the atoms that make us up. And even in 1995, this was a big puzzle, but it all changed in 95. And for the last 10 minutes of my talk, I'm going to talk about how it all changed and started telling us a different story, which has this bearing on the future of the universe. So remember, we have the Hubble's law. Here's a much better version of the Hubble's law. And this comes, as you can see, you measure distance to a galaxy and you measure its recessional velocity, and they lie on a straight line, and that tells you that the universe is expanding. And the slope of this line tells us how fast the universe is expanding. And this, because these are galaxies that are near us, this tells us at the current time how fast the universe is expanding. Now you can ask the question, has the universe been expanding uniformly at the same speed all through its existence? Right? And the answer is possibly not. And this is exactly what Hawking was trying to say when Hawking was saying, if the universe is expanding, is it going to slow down and come back, or is it going to go faster and faster and faster? Whatever. Hawking didn't know, but now we can find out. And so in order to find out, we have to know whether this line stays like a straight line if you go further and further. Here you're going out to only, the distance between normal galaxies is about a megaparsec. You're going out to 50 megaparsecs away from us. This is really the nearby universe. You have to go very far away. And in astronomy, if you go very far away, you go into the past, right? Because you're looking at galaxies from which light takes a long time to come to you. So if you want to find out about the past of the universe, you go very far away. The further you go away, the more past in the universe you go in. Joto dure jao na keno, if you go very, very far away, then they are telling you about the past of the universe. So you want to know in the past of the universe, say when the universe was half its age or 1/10 of its age, how fast was the universe expanding? In order to do that, what I have to do is to go very far away and measure the same Hubble law, the relation between the velocities of the galaxies and the distance. And if I can find that it was different, then I can figure out how the universe's speed of expansion has evolved. Now, till 95, we couldn't do this because we couldn't measure the distance to far away galaxies. How far away can we detect the expansion? To measure the distances to galaxies, we need something called a standard candle. A standard candle is something like this. If you know, for example, a light bulb or a candle which has for which we know how bright it is. For example, I know it is a 100-watt bulb, and you take it at different distances away from you. Then, if you measure how much light is coming to you, then you can find its distance. And this is how we use distances in astronomy. And I didn't tell you all about it. For example, Hubble used something called Cepheid Variables, which were known. These were variable stars at that point, which were known as standard candles. From the properties of their oscillations, you could find out how bright they are, and so you can find their distances. But those things are very limited, have limited use. You can't go very far away and measure these distances using these variable stars because you can't detect them in galaxies very far away. But that changed in 95. What changed in 95, and that is what changed was, we found that there was something called type 1a supernovae. Supernovae are things that happen when stars go explode. And we found there's a kind of supernova, which is called the type 1a supernova. And if you find them in a galaxy, you can actually find them outshining the galaxy. You can find them as a big blob, even in faraway galaxies. And they are standard candles because they reach a peak that is that can be predicted, that can be known. And once you find what the peak brightness of this supernova is, then you can find away how far away it is. And so you can measure it. For example, a supernova happened, type 1a happened in 1987 in our nearby galaxy, the Large Magellanic Clouds that I showed you before, one of the satellite galaxies that I showed you in the Chile picture. So this whole program started of finding supernovae in external galaxies once it was known. So now what is done for the last 20, 25 years, this is being done in that people have been studying parts of the sky. Say a typical telescope will take 50, 100, 200 fields and find and take pictures and come back every night to take a picture at the same place over and over again. And by digitally comparing these images, you can find out how what has changed. And if you can find one of these supernovae, it will appear as a big blob on the galaxy, and you have to catch it before it reaches its maximum. Then bigger telescopes are all informed, like the Hubble Space Telescope, etc. They take a spectrum, they confirm it to be a type 1a supernova, and then if you measure the top of the supernova, how the peak of the supernova, then you know exactly how far away that galaxy is. This is the way of finding the distance. The telescope I showed you in this particular picture, that's the Magellanic Cloud, by the way, is one of the telescopes that is being used to do this. It's the 4-meter Blanco telescope in Chile. It's called the Dark Energy Machine now. There's something called the Dark Energy Survey, which is being done with this telescope, and it does this. It takes pictures of the sky automatically. It's being optimized for it automatically every night, and night after night after night, these pictures are compared, and we can discover thousands of supernovae every year. When I was a student, we would be lucky if we could find maybe 20, 30 supernovae in a year, but now these can be found. And we are trying to measure distances to galaxies and mapping out this Hubble plot till very far away. I'll give you an example of such a thing. You can see that if you compare these two pictures of the sky taken with that telescope 3 weeks apart, with the naked eye, it is very hard to find where the supernova is. But if you subtract one from the other, you will see that that's where the supernova was. This can be completely subtracted off, and that galaxy had a supernova. As soon as that was found, you call the Hubble Space Telescope, they will take a wonderful picture, and you can have a nice picture of the supernova just outside the galaxy, and then a spectrum of it could be taken. This is a good example. So going back to Hubble's law, if you remember, Hubble's plot from 1929 was pretty pathetic, because it was only the nearest 20 or so galaxies, but then there was a lot of scatter. But I showed you a plot from 95, and if you look at all the galaxies in here, they will fit into that little yellow plot, yellow part of this plot. But the scatter has gotten a lot better. This is before finding supernovae as standard candles. Even then, people were using variable stars and various methods to map out the Hubble flow, and even going out to about 500 megaparsecs or so, the curvature of the Hubble plot had not been found. That yellow thing just shows how many galaxies Hubble had found. But you can see now if, for example, the expansion of the universe is slowing down, that means in the past the expansion of the universe was faster, which means that the slope of this curve would be much higher, right? And that is what people expected, because you know that the universe is not empty. Universe is a lot of matter, so the universe is going to pull back the expansion. But what this whole thing found was that just the opposite. Of course, this led to a Nobel Prize recently of the discovery. This discovery was that we found that as you go further and further away, this slope Hubble slope. Instead of going steeper in the past, actually went the other way, which means that the universe was slower in the past. And that means the universe is actually speeding up. Remember, Hawking talked about all those possibilities of the universe coming back, etc., etc., etc. This was not in one of them. In fact, that is why you should throw away Hawking's book now. It's all redundant, because now we've found that the universe is speeding up. The universe was slower in the past, and as a result, and right now it is accelerating. Right, and this is why you can see that as you go further and further away, the slope of the Hubble line is actually going down, not going up. And so the universe cannot recollapse at all. In fact, the universe is going to become a much emptier place, a much bigger place. The future of the universe is going to become much larger, much faster. And so this is the big surprise of the universe. The surprise of the universe is that the matter that we are made up of quarks, is actually only 5% of the entire matter energy of the universe. Dark matter, the kind of matter that you found by gravitational lensing or by the rotation curves of galaxies, is only 25%. And the rest of it, about 70% of the matter energy of the universe, E equals mc squared, so matter and energy are the same, is in this very odd kind of energy that we've discovered, which is pushing the universe, making it accelerate. It is not like gravitation pulling it back, it is actually pushing it. So it is something that is opposite of gravity. I don't know who called it dark energy. It's not a very good name, but that's the best name we have. So we now know 70% of the energy of the universe not even gravitates, doesn't pull it. And that is why the universe is accelerating. So what is going to happen to the universe? The universe, normal mass, would have made the universe decelerate, but now it seems to be accelerating. And so it has negative pressure. And so as a result, all that is not going to happen anymore. Remember, and what will happen is that the universe will probably become a much larger place. People are calling it the Big Rip. It might, at some point, the universe will get so big, it'll rip itself apart. That's the future of the universe. I'll stop there and see if there are any questions. Thank you very much.
Thank you, sir. So we have some question in the comment. So if you allow us, so we can start our discussion session, sir.
Yes. So okay, what kind of comments do you have? Are you going to read out the comments, or somebody will? They will ask.
I'll add in the screen. You can or read out. So does dark energy responsible for expansion of universe?
Achha, so what is the question again? Please repeat.
Does the dark energy responsible for expansion of universe?
Yes. So the idea is that this dark energy, we don't understand what it is. It has negative pressure, we know that. And if you go to a physics journal now, lots and lots of models are being made up what this dark energy is. We know that it is not gravitating matter, right? It is not, but dark energy is not making the universe expand. The universe would have expanded without dark energy. The universe is expanding because it started off with a big bang, and it was expanding anyway, right? It started off from a very small place, and the initial impulse that was given to it made it expand. So it's expanding. What dark energy is doing is it's making it accelerate. It's making it faster and faster and faster. What would happen is if the universe is expanding like this, and the matter, all the matter in the universe, which is gravitating, would have pulled it back or even slowed it down. Like when you throw a stone up in the air, it would go and slowly slow down and then come back. But this is something that's pushing it away from you. So dark energy is making it accelerate. It is not making it expand.
Sir, thank you, sir. We have another question. How can we calibrate the color of the cosmological body when we're getting the radio signal in the telescope?
In what context are you asking this? I mean, so maybe calibrate the color. I don't
Yeah.
understand the question.
Okay, how can we calibrate the color of the cosmological body when we getting the radio signal in the telescope?
Okay, so I don't understand the question, but I can make some sense out of this. Say if you're getting a radio signal of the in a telescope, then it is a radio telescope, right? And so because different parts of the spectrum, I showed you the spectrum, the Bernoulli, এবং তার নানা জায়গায় actually you can ask the question in Bengali if you have a problem in expressing yourself. But
Yeah.
so say it's a radio telescope and it's radio and it's observing the object. Now color is nothing but it is the ratio of the brightness of the object in two different wavelengths. So for example, you have blue wavelength and a red wavelength, and something that is blue will give you more light in blue than red. And so you take the ratio of the two, that gives you color. So at radio wavelength, it is the same. If you can observe it at 2 or 3 different frequencies or wavelengths in radio, and you take the ratio and you can find its color. I think that's how I understand this question.
So another question, sir, why some galaxy there is not going away like other?
Good, very good question. What is happening is, see, the universe is expanding. So as a whole, all galaxies are going away from each other. But there is gravitation as well. So galaxies that are, and remember, gravitation goes as m squared, over r squared.
Yeah.
So if there are two galaxies that are very far away, then their gravitational force is not very large. And so they can float with the universe and go expand with the universe. But if there are two galaxies that are very close by, then the gravitational force between them is much stronger than the force due to the expansion of the universe. And this is why our nearest galaxy, I told you, Devjani, Andromeda, is coming towards us. It is falling towards us because we are pulling it. And we are close enough that our gravitational attraction is more than the force due to the expansion of the universe. This is why in Hubble's plot, he found 3 or 4 galaxies which have negative redshift. And they are all falling towards us because they are attracted by our galaxy. But if you go a little further away, then because of 1 over r squared, the force is so small that the expansion of the universe dominates and they cannot be pulled back.
Okay, sir. Thank you, sir. We have another question. How can we get the exact size of the Milky Way galaxy, whether we all human being are part of the galaxy?
Very good question. What has happened is that you can make maps of the stars. Now, I did not talk about this at all, but you can, for example, go to the web and look up Gaia, Gaia. Gaia is a satellite which has been now measuring distances to stars, about 1 million stars, 10 lakh star, in our Milky Way, and measuring distances by a method called parallax. And it is a satellite that is going around and it's measuring how far away the stars are from a method called parallax, and thus making a 3-dimensional map of the galaxy. Right now, Gaia is up there now. Before this, we had Hipparcos, another satellite. Before that, we used other methods. But the whole point is to measure distances to stars to make up a 3-dimensional map. And once we make up a 3-dimensional map, we know how far, what is the shape of these spiral features that I showed you, and how large the galaxy is.
So thank you, sir. We have another question. So the question is that a few days ago, scientists observed a halo coming from an Andromeda galaxy, extending for more than 1.3 million light years. So that does it signifies, and sir, does our galaxy and Andromeda galaxy will collide someday?
Of course. So I didn't show this to you. I mean, in fact, if you Google my name and collision Andromeda Milky Way, then you'll find nice pictures and simulations of these. I did quite a lot of work on this, and my friends have done quite a lot of work on this. And we found that as Andromeda and us are coming towards each other, and they will collide with each other in about 4 billion years. So it won't happen tomorrow. There's quite a lot of time there. But what happened was Andromeda and us, the two galaxies, have expanded with the universe and have gone up to about a megaparsec away from each other. A megaparsec is about 3 million light years, 3.25 million light years, and then it has started to come back again, and it's falling towards each other. Andromeda is falling towards us now at a speed of about 120 kilometers per second. And if you do that calculation, you will see that they will collide with each other and form one galaxy eventually in about 4 billion years. And this happens everywhere. You can see galaxies colliding with each other. So and in this process, what will happen is that we will pull out some of the strands from stellar strands from Andromeda, and Andromeda will pull out some stars from us. This is already happening. We can see they're called streams. And we have already detected such streams. The one that you heard about recently is one of these stellar streams. This is because of the close interaction that is happening between us and Andromeda. Not just that, there are these interactions happening. We know of about 40 different satellites of the Milky Way. We know about 45 satellites of Andromeda. They are interacting with each other, also pulling out stars from each other. All that is happening. So it's a very active, this system.
Thank you, sir. So we have a question, different type of question. So can we describe the Big Bang via spirituality?
Big Bang and what?
Via spirituality.
Spirituality.
Yeah.
That's a very difficult question to ask. That is not my subject. But I'll tell you a story. The Big Bang was actually postulated by a Christian priest. He was a mathematician, a very famous mathematician called Georges Lemaitre, who was a Jesuit priest, a Catholic priest. He was also a professor of mathematics at the University of Sorbonne in Paris and a very good friend of Einstein. Now, I know this because I was taught in Kolkata by Father Goro in my school. I went to a missionary school who was a PhD student of Father Lemaitre. Father Lemaitre in Paris. Father Lemaitre did this whole, what he did was he solved Einstein's equations and found that the universe was expanding. And it is his model that we are now studying. So after he did that, now Einstein did not believe in this at all. Einstein did not think the universe will be expanding. Einstein thought the universe is static. So they had a famous fight in 1932 at the Solvay Congress in Belgium. Father Lemaitre got up and gave this paper in which he showed that the universe will be expanding. And here, this didn't come from his religious belief. This came from his mathematics. And Einstein got up and said, Father Lemaitre, you're a Christian priest. You remember Einstein was an atheist. Einstein was a Jew and also an atheist. He did not believe in religion. He said, you are a Christian priest. Just because your religion says that the universe starts from one point, God created the universe. That is why you are saying all this. This is not true. Your mathematics is wrong. And Einstein changed his equation. And then many years later, he understood that he cannot change his equation, and Father Lemaitre was right. So Father Lemaitre was a very remarkable person. He was a priest, he was a religious person, yet he did the Big Bang. And he was one time asked, and this is why I raised this story, he was one time asked, Father, is your religion related to this finding that you have found? Because Einstein had accused him of doing that. And Lemaitre said, in my life, I see these two things as completely different. I don't see how one affects the other, because my religion helps me understand the answer to questions that are different from the mathematics and science that I do. And they help me understand the questions that are different. So I think the Big Bang does not come from any religious belief. It came from pure mathematics. And whether somebody in their spirituality can make some sense out of Big Bang or dark energy or dark matter is a personal matter. These are completely different things, and I think they address completely different questions.
So thank you, sir. So there is another request. No, this is not a question. So he request us to request you to tell about the black hole and the gravitational waves and the
Hey,
fast imaging of M81 black holes. So
okay,
he,
but I didn't talk about that today. That will take me another whole talk to give. Maybe I will come back some other time and give
okay,
you a full talk about that. Okay, let
okay,
me do that.
yeah,
Maybe
okay.
talk 100 of this series. I will talk you about the M87 black hole.
Thank you, sir. So there is another question. So nowadays we know that our universe is expanding, not only expanding but also accelerating. Is there any possibility that our universe would get shrink after a certain period of time? Of course, time is in light year unit. So
Of course not. Because what we are finding now, the universe is accelerating. So what will bring it back? How can it shrink? This is exactly what I said. In my
yeah,
entire talk, I said before we discovered the acceleration of the universe, there was some belief that the universe can be brought back by the matter. Now we know that there is much more of this dark energy than matter. And so it has already overwhelmed the effect of matter, which is the only thing that it can bring back. So now there is no way the universe can be brought back.
okay, sir. Thank you, sir. So there is another question: are we made up of dark energy?
No, not at all. In fact, we are not even made up of dark matter. I
Yeah.
told you that we are made up of the elements in the periodic table, which are made up of quarks, etc. We know dark matter. We can sense dark matter from its gravitation, but we know it is not made up of quarks. We don't know what it is made up of, and dark energy is completely different.
Different.
It is something that is totally different. Yeah.
So thank you, sir. Will it not violate the thermodynamics? So something like when the entropy will be maximized in this ever expanding process. So I don't.
No, not
So
at all. That in you know it's
different.
entropy, increase of entropy cannot be violated.
Mhm.
So whatever is happening, so for example, even if you forget about the acceleration of the universe, etc., I was saying that as the universe expands, it cools. Why was I saying that? If you think of adiabatic expansion in thermodynamics, that is what happens. If something expands, it cools, right? And certainly entropy increases in that. You simple first year physics adiabatic expansion does that, right? Now, if it's expanding at a faster and faster rate, then the entropy of the universe will go accordingly. There is no violation there.
So thank you, sir. So can you tell about the cosmological microwave background? What is the significance?
Right. So that is another topic of another talk, but very briefly, I can say that what happens is that the universe started with a Big Bang, Father Lemaitre's Big Bang, for example, and then and then it has started to expand. Now, at the beginning, there was only energy, right? When the universe, and then as the universe expanded, the universe started cooling down, and so matter, etc., started from there. And as the universe was so big, it cooled down to temperatures that came below a certain point. Then energy converted into matter. It became first protons, neutrons, and then those protons and neutrons and electrons got together to make hydrogen atoms, and then hydrogen atoms got together to make molecules as the universe cooled, right? So, but from the very beginning of the universe, there's a lot of energy. That energy is left over. Some of it is left over. Some of it never became matter. So that amount of energy that is still left over, and this universe is now so much bigger compared to what it was at the beginning, that energy that is left over is the cosmic microwave background. And I haven't told you this whole story, but you can
Yeah.
read about it. George Gamow, for example, in the 1930s, 1940s, actually, from by calculating, showed that if this amount of energy that's left over will be at a temperature of about 3 or 4 degrees Kelvin, and we have found out that this energy is a black body with a temperature of 2.7 degrees Kelvin. So it actually completely fits into the Big Bang theory.
Yes, sir. Thank you, sir. So we have another question, sir. So we know that our universe is expanding, is it constant value of expanding or universe or not random value?
It's not. I mean, that the whole point of my talk, you missed that, because I said that the universe was expanding at a much lower value. The expansion rate was lower, and now it is accelerating, right? So the expansion of the universe is changing. The Hubble expansion itself was expanding slower. Now it's faster, and it's getting faster and faster.
So thank you, sir. So we have another question. Since there is no direct evidence of dark matter or dark energy, but how can we take into account with confidence that dark matter and dark energy are contribute 25% energy and 70% energy respectively? So
I only showed you one way in which the dark energy has been measured. Now there are 4 or 5 different ways in which the dark energy has been measured. Cosmic microwave background fluctuations, I haven't talked about that. That has showed us the amount of dark matter and dark energy. There are measurements not from just supernovae, but from galaxy clusters. There are other things. Yeah, and from dark matter, I showed you 2 different ways. I showed you the rotation curves of galaxies. I showed you gravitational lensing. There are 10 different other ways that dark matter can be measured, from the dynamical ways of things moving, or from X-ray emission from clusters of galaxies. I didn't go into all of that. So we are not, we are confident because we have measured the same thing in many, many different ways, and they all give the same answer.
Yeah.
Right. So that is how in physics we get confidence in something. Of course, doesn't mean that when we make a measurement, it can turn out to be wrong, of course. And that is why, in order to believe something, you have to repeat the experiment many times and use different methods by different groups. And this is what I showed you is now what we believe. Of course, it will change, because some other people will make more measurements, and that 5% will become 4.7%. And that dark energy 70% will become 73%, something like that. But it will not go away.
Thank you, sir. So how can we measure the fringe shift? How can we experimentally measure the fringe shift for Doppler effect as a star is moving?
It's not the fringe shift. It's not fringes. It's lines, emission lines or absorption lines in the spectrum. So rekha. So these things move, and we can measure it by spectrographs. There are many kinds of spectrographs. For example, if you're a physics student in the lab, you will use a Michelson interferometer, for example, or you can use various ways of, you can use a grating in which you split the Bernoulli, the spectrum, into different lines, and then that grating is calibrated, so you can measure the wavelength by rotating the grating. And so you use things like Young's double slit experiment, for example, or a grating in which you can measure by rotating the grating, you can measure how much the line is moving, and as a result, you can measure. So these are very standard ways of measuring the wavelength in a spectrum. And so the same thing happens for a spectrum of a star or a galaxy. You pass that light through a telescope, and at the end of the telescope, there's a spectrograph, which has a prism or a grating or a grism, something like that. And that light, as it passes through the grating, then falls on a detector, and on that detector, we can measure the shift.
So thank you, sir. We have another question. Why not the Big Bang in different places? And in this way, we avoid the goods inflation.
I don't understand this question.
Okay, so we have another. We can. So, do you believe the Big Bang automatically happened?
The Big Bang.
Yeah.
Yes. Yeah. Who else will make it? I think the Big Bang happened, and I don't think this is the only Big Bang. There are lots of theories about the multiverse, for example, or multiple Big Bangs and things like that. We might not live in the only universe. So in our universe, it started with the Big Bang, but there might have been universes before us. There might be universes in parallel to our universe. But yes, I believe that the universe automatically happened at the Big Bang, and there are other Big Bangs that are going on, outside our universe also, which are automatically happening.
Thank you, sir. So this may be the last question of this discussion session. What will be the final condition of galaxy after accelerating expansion?
Yeah, so this is what this slide that you're seeing says. What will, that's the future of the universe. In the future of the universe, as the universe expands, it becomes such a big place that eventually it becomes a very cold place. The light density of the universe is very small, and as the space becomes larger and larger and larger, it rips apart all the matter that is together. So eventually the atoms themselves are ripped apart, the earth explodes. But this will happen, many tens of billions of years later. You don't have to worry about that now, but you can see at the end of this plot, you can see the earth explodes, the solar system breaks apart, because eventually the expansion of the universe becomes larger than gravity, and then the solar system breaks apart, and it becomes larger than the forces that are holding our body together. These are the forces of cohesion, and so our bodies also rip apart. But I'm not going to be there at that time.
Okay, sir, thank you. So I got another question, if you allow, then I can read this, maybe the final one. Is it possible to find of the center of the Big Bang of our universe?
No, because there is no center. There's no center because, think about it this way. If you take the whole universe and you play it like a movie that goes backwards, it goes back to a point. So every point in the current universe maps back to that point. So the Big Bang happened where I am sitting. The Big Bang happened where you are sitting. The Big Bang happened where, I don't know, President Trump is sitting. The Big Bang happened in the Andromeda Galaxy. The Big Bang happened everywhere, right? So every point in the universe is the center of the universe, because they all map back to one point at t equals 0.
So thank you, sir. As we don't have any questions, so we can conclude our discussion session, sir. So yeah, we have enjoyed a nice presentation, and I think our students have enjoyed lots and learned a lot of things, sir, by this webinar, sir. And so we would like to thank you on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. It's our honor and privilege, sir, to host you in our International Physics webinar, sir. And hopefully in near future we'll arrange another webinar with you. So thanks again, sir, and bye for today. So আপনাকে অনেক ধন্যবাদ, স্যার। আপনি আমাদেরকে সময় দিয়েছেন। আমরা জানি অনেক ব্যস্ত আপনি, তারপরও আমাদের ছাত্রছাত্রীদের কথা চিন্তা করে আপনি আমাদেরকে সময় দিয়েছেন। তার জন্য আমরা আপনার কাছে অনেক কৃতজ্ঞ, স্যার। ভালো থাকবেন।
খুব ভালো লেগেছে।
নমস্কার, স্যার। ভালো থাকবেন। বাই, স্যার।